All right. So I believe we covered everything there is to cover about AC analysis using phasors and the concept of impedance and admittance, and then also the concept of phasor diagrams. And all is left is just to apply the techniques that we already know from circuits one using those new concepts. So all that is left is to just go through examples so that you understand how the old techniques that you already know apply with those new entities that we have defined, mainly phasors and impedances and admittances. The things that we learned in DC analysis, which is how to analyze circuits with resistors and then DC sources, right? So we know how we have a bunch of techniques that we can utilize such circuits. We can do the same thing for AC steady state analysis. But what fills in for resistors now is impedance. It's a complex value. And what fills in for the sources are, instead of sources, now we have phasors. The sources that are signals in the time domain. We have T domain. We have now phasors that are signals in the frequency domain. Right? And the whole slew of techniques that we know for DC analysis now apply for AC analysis with those kind of like augmented concepts. The concept of impedance that augments resistors, and the concept of phasors or phasor signals that augments the source signals in the DC analysis domain. Right? So the techniques that we've learned in circuits 1 are like Ohm's law, which when applied to phasors just applies directly to the phasor equations. So it's going to be V phasor equals I phasor times the impedance. And then we know the rules for calculating impedances in series, admittances in parallel, right? We know how to do current and voltage division from networks 1, right? If you have a voltage divider, you know how to do that. If you have a current divider, so I have a current that's divided between two resistors, you know how to do that, right? And then KVL and KCL, the cornerstones of circuit analysis, right? And then those are the basic techniques. So those are basic. And then there are more involved, or I would say more advanced arsenal at our disposal, such as nodal analysis, mesh or loop analysis, superposition. If you don't remember any of those concepts, you have to review them. Source exchange, and then finally the big network theorems, the Thevenin and Norton theorems. Okay, so we'll do a bunch of examples where we touch on those basic techniques, and we touch on the more advanced circuits techniques that, and there's nothing here. We've already learned those in circuits 1. All we have to do now is to show how those techniques apply for the case where we are doing AC analysis, where we have phasors for sources and impedances for resistors. Okay, so let's do one example. So say we have this circuit. Vs equals 24 volt, 60 degrees. Then we have a resistor, 4 ohms. We have an inductor. The impedance is already calculated at 60 hertz to be for you to be J6 ohms. You don't have to do that calculation. So what would, if someone asks you what would the inductance of this be, and you know that the frequency is 60 hertz, right? You can find the inductance from the formula J omega L, right? So it's going to be 2 pi 60 L equals 6, and you find L being 6 over 2 pi 60. That's how you find the inductance, right? And then the rest of the circuit. The rest of the circuit is there's an 8 ohms and there's a capacitor. Capacitor will always have a negative impedance, negative reactance, so the imaginary part will be negative. So it's going to be minus J4 ohms, right? And this goes here. And then we want to calculate I1. Of course, it's a phasor because we're doing AC analysis. I2, and then I3. And then we have to calculate V1 and then V2. And we want to use like our basic circuit analysis techniques. So what we'll start with, we'll find Z equivalent seen by Vs. And again, this is one way of solving this. There are always going to be multiple ways of solving the same problem. Whatever you find easier, you can use, right? So Z equivalent is what is seen by Vs, and it's just those two impedances in parallel and this in series. So I would write it. Okay, let me give you the steps first. After we find Z equivalent, we use that to calculate I1. After we calculate I1, we use KVL to calc V1. After we calculate V1, we use V1 to calculate I2 and I3, which is easy to do. And then after we calculate I3, we calculate V2. So this is the step. We find Z equivalent, we calculate I1 using Ohm's law. We use KVL to calculate the voltage across this inductance. And then we use that to calculate I3 and I2. Let me call this I3. Let me call this I2. And then we use I3 to calculate V2, the voltage across the capacitor. So let's start with Z equivalent. What is Z equivalent? Z equivalent is 4 plus 2 parallel connections of impedances. So it's 4 plus, so we have two branches here. We have first J6, and J6 is in parallel with the second leg, this leg, which is 8 minus J4. So it's going to be 8 minus J4. So that would be the Z equivalent. We just calculate it now. It's going to be 4 plus, we know how to do two impedances in parallel, right? So it's their product over their sum. J6, 8 minus, right? So you know how we get that, right? 1 over Z equivalent equals 1 over Z1 plus 1 over Z2. And we call this ZP. So if I do the math, I end up with Z1 plus Z2 over, multiply this by Z2, Z2, multiply this by Z1 times Z1. I end up with Z1 plus Z2 over Z1, Z2. That's where this comes from this expression that we already know, right? So it's going to be 8 minus J4 over J6 plus 8 minus J4. Their product over their sum. And we can do this calculation easy, right? We end up with 8.235 plus J4.941, and I chose to approximate up to 3 significant digits. Anything beyond 3 significant digits, I just round off. I can write this, convert this to polar, so I get 9.604, 30.96 degrees ohms. Okay. This is the equivalent impedance, and now I can calculate I1 directly. I1 is just the voltage, using Ohm's law, I1 is just the voltage over the equivalent impedance. So I1 as a phasor is just going to be Vs as a phasor. This is just like DC analysis, only it's more cumbersome because now you're multiplying and dividing complex numbers. So it kind of gets annoying plugging this into a calculator. And I remember that was when I took this course. When did I take it? When I took this course in like 1997, that was the most annoying part for me. Is going through those those lots of complex number manipulations. Okay. All right. So this is Z equivalent, which is 2460 degrees over 9.604, 30.96. Subtract the angles, do the division of the magnitudes. I end up with I1 being 2.499, 29.04 degrees. Okay, I found I1. Now using KVL, I know how to find V1, right? The voltage drop across this loop is 0, right? So V1 is going to be Vs minus the voltage drop across 4 ohms, right? So Vs minus the voltage drop across 4 ohms due to I1 is going to give me V1. So and this is obtained directly from KVL. So V1 is going to be Vs minus 4, which is the resistance, I1. And again, we have to do the manipulation. 2460 degrees minus 9.996, 29.04 degrees, and then you go to MATLAB or your calculator that might do complex numbers, and then you have, I mean, you cannot sum this, you can sum this directly, but you have to convert this to rectangular form because it's easier to sum in rectangular form, right? Yeah, so in your calculator, what you would do is you would say, hey, the real part is 24 cosine 60 degrees minus 9.996 sine 29.04 degrees plus j, and then the imaginary part is going to be 24 sine 60 degrees minus 9.996 sine 29.04 degrees. That's how you would do it. And you do the number crunching, you end up with 3.261 plus j 15.932, and then I transform that back to polar. I get 16.263, again using MATLAB, 78.43 degrees. So while preparing those the notes for the lecture, I kind of did all those in MATLAB. And I kind of like chose to, so that I'm not repeating the book, I chose to go to 3 significant digits. So that's why you'll see some discrepancy from the example in the book. Right? But I mean, depending on the problem, it's okay if you want to go to 2 significant digits. That's also okay. Right? So it's I wouldn't advise going less than 2 significant digits, because if you do that, the errors are going to compound as you do the calculations. You don't want to do that. You want to minimize the errors, the rounding errors. Okay, so that's V1. So we solved for I1 and V1. I1 and V1. I2 now is going to be V1 over the impedance and I3 is going to be V1 over the other branch, the impedance of the other branch. So I2 is going to be V1 over J6, that's the impedance of the inductance. That's going to be 16.263 over 6, 78.43 degrees. J is in the denominator. J has an angle of 90. Taking the numerator, I end up with minus 90 degrees. So I end up with 2.711 minus 11.57 degrees. I3 again is going to be V1 over the impedance of the other branch, which is A minus J4, which if we do the number crunching, turn this into polar, do the division, blah, 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 all of that, I end up with I 1.818, 104.995 degrees. Right? So V2 in this case is going to be just Ohm's law. V2 is the voltage across this capacitor. It's going to be just Ohm's law. It's going to be I3 that we already calculated times minus J4. So it's going to be 1.818 times 4, and then the angle of I3, 104.995 degrees. What's the angle of minus J? So this is J, minus J is here. The angle of minus J is minus 90, right? So times minus J and minus J has a magnitude of 1. So the magnitude will be 1 and the angle will be minus 90. So we sum minus 90 degrees. So we end up with 7.272 and the angle is going to be 104 minus 90. It's going to be 14.995 degrees. Okay. If we plot the phasor diagram for all the currents that we found, so this is the complex plane. So I1 has a magnitude of 2.5, about 2.5 and 29 degrees. So it's going to be 29.04 degrees. I2 is going to have a magnitude of 2.7, close, but it's going to have an angle of minus 11.57 degrees. This is I2, I1. And then I3 is going to be about 105, have a magnitude of 1.81. So this is not exact. This is just an approximate phasor diagram, right? And then we can see that KCL applies in the sense that I1 as vector addition, I1 equals I2 plus I3. It needs to be for KCL to apply. I1 equals I2 plus I3. But now the currents are not real numbers. The currents are complex numbers represented by phasors, which are vector-like. So KVL is true, right? But it's true in the sense of vector addition, meaning like I1 plus I2 and I3 added as vectors should give me the zero vector for the complex number that is zero. You can double check that. I mean, we used that to do some of the calculation, but and it is evident from the phasor diagram that if we sum those three, we get zero. Okay, but there's something nice to check numerically. You might not get exactly zero due to rounding errors. That's why rounding is when you're doing a lot of complex multiplications and additions, and you're using solutions of sub-solutions to get other solutions, right? So you're solving the problem in stages. When you do it that way, round-off errors tend to accumulate. That's why when you sum this, when you actually sum what you've got, you might not get exactly zero, but you should get some small value that represents the round-off errors. And the more significant digits you take, the more accurate this will be, the more close to zero it will be. All right, let's do another example. To solve this problem, so this circuit, we want to solve the circuit and we want to solve it in the numerous techniques that we learned in circuits 1, in networks 1. So we have this circuit, 1 ohm. At 60 hertz, this inductor has an impedance of J 1 ohm. And I have a current source. Current source is 2, 0. It's represented as a phasor, amps. I have a voltage source of 60 degrees volts. And then I have 1 ohms, and then I have, I'm trying to, what I'm solving for is the current through this resistor. And then I have 1 ohm, and then minus J 1 ohms. Right. Like I said, we want to demonstrate how we can utilize all the different techniques we learned for solving circuits in AC analysis. And the first thing we want to try is to do nodal analysis. So this is a bit of more involved circuit. Notice it has 3 loops, 3 meshes, it has a lot of nodes. So let's review nodal analysis. What do we need to do for nodal analysis? Well, first we need to designate a node as a reference node, right? And then we found a voltage source. And we need to designate the nodes, right? The nodes are V1 and then V2. Notice here there's a supernode, meaning that there is a voltage source between 2 nodes. So the way, if you remember, the way to do the analysis here is to designate those 2 nodes and the branch between them with the voltage source as a supernode, right? So we apply all the KCL, right? We apply KCL to that supernode, meaning the sum of all the currents coming out of the node should be 0. That's the application of the KCL. That's the first step in writing the nodal equations, the node equations. So what are all the currents coming out of the supernode? Well, first we have this, right? So it's V1 over 1 plus J. Then we have this current, right, which is minus 2, 0 degrees. We have this, which is plus V2 over 1 ohms. Then we have this current, which is plus V2 over 1 minus J equals 0. This is equation 1. And then equation 2 we get from the constraint equation between V1 and V2. It's just, we know that just V1 plus this voltage source gives me V2. This is called the constraint equation. So this is how you deal with the supernode in nodal analysis. And ultimately what we want to get is we want to get 2 equations for the 2 unknowns, for the 2 unknown nodes. Right? It's helpful to write this in matrix notation so that we can solve it. Right? So I can move the minus 2 to the other side. I can move the 6 to the other side. I can move V1 back to the left-hand side. Then I can write everything in matrix form. So in matrix form, I end up with this equation. So this is V1, V2 equals something. Right? I'll name the matrices and the vectors, column vectors in a suggestive manner. Right? This is V, so I'll name this W. W times V gives me I. I'll name this I. That doesn't mean that this is necessarily current or this is necessarily admittance. This is just how I named those matrices and vectors. Right? So from equation 1, it's clear that I just have 1, it's V1, 1 over 1 plus J times V1. And then I have, what's multiplying V2? I have 1 plus this term, so it's 1 plus 1 over 1 minus J. That's times V2, right? That gives me what? Take 2 to the other side, that gives me 2. 0 degrees, I can't forget about the 0 degrees, right? And then I end up here with V1 has a coefficient of 1. Take this to the other side, it becomes minus 1. This gives me, take this to the other side, it gives me minus 6. Okay, so this is what I need to solve. And really, V1, V2 is just going to be Y inverse, the inverse of the matrix, times I. So this is matrix multiplication. Okay, we can easily do this in MATLAB. Let me do this now. All right, so let's plug in the values, the values for the matrices. Right, so Y equals, and if you are not don't remember exactly how to use MATLAB, I suggest you kind of practice it. You need to be able you should be able to know how to plug in matrices and row and column vectors in MATLAB and do all the linear algebra stuff that you need to do, like matrix inversion, matrix multiplication, and all of that. Right. So the first element we said is 1 over 1 plus j. Second element is 1 plus 1 over 1 minus j. Simple, I'm just plugging things in. And then I go to the second row and I have 1 minus 1, right? And this shows me it does everything for me. It calculates, sums everything up for me and gives me the matrix. And then I want to put in the column vector, right, which is on the right hand side. So that's going to be 2, and then I go to the second row, minus 6, that's I. And then we said that yeah, V1 and V2 is just going to be inverse Y times I. Okay, so so this would be V1 and V2. The first row of this result is gonna be V1 phasor, and the second row is gonna be V2 phasor. Let me actually store this in a variable. Let me call this V. Okay. Now I want to take the magnitude of this, so absolute, because I want to represent everything in polar form. So absolute V. So that's the magnitude. And then the phase, I could use phase function or angle function. Oh, what did I do? I think the angle is the function is called angle. Yeah, angle V. Okay, this gives me the angle in radians. What I want is to get the angle in degrees. So I divide by pi and then I multiply by 180. That gives me the angle in degrees. So let me write that down. The magnitude for V1 is going to be, so V1 is going to be 3.808 with an angle of minus 156.8 degrees, and then V2 is going to be 2.916 with an angle of minus 30.96 degrees, and then I0 is just going to be V2 over 1. So I0 is going to be the same as V2. So we said after we solved this in MATLAB, we got V1 equals 3.808 minus 156.8 degrees, and then V2 is 2.916 times with an angle of minus 30.96 degrees. So we said I0 from the circuit is just going to be V1, V2 divided by the impedance, which is 1 ohm. So clearly I0 is going to be just V2 divided by 1 ohms. So I0 is going to be 2.916 minus 30.96 degrees amps. And we solve this problem using nodal analysis. Next, we want to solve this problem using loop analysis. As a reminder of that technique, Okay. Let's look back at the circuit and select the loops. So the circuit looks like this. 1 ohms. Let's just draw it. Right. One ohms, and then this is what we're solving for. And then I have 1 ohms minus J 1 ohms, right? So I need to select the loops or the meshes, so to speak. So I could have done this I1, I2, I3, but that wouldn't work in the same way that we had to when we did nodal analysis, we had to select a super node, this node, uh, because of the existence of the voltage source. In the same manner here, we have to select a super mesh or a super loop, because I mean, out of those two loops, we only get one equation, which is I2 minus I1 equals 2. And we need to get 3 equations to solve I1 and I2 and I3. So we need to kind of get the super loop instead of those small loops. So what we do is we keep this is fine, I1, but then we select the bigger loop, what's called the super loop or the super mesh, which is this one. So this is I2, and then I3 is this mesh, this loop, I3. You can call it mesh or loop, it's fine. Okay, and after we stated the loops, all we need to do is we just apply KVL for each of the loops, right? So starting, of course, because this current source simplifies things, it gives us just a constraint equation. It tells us that I1 equals minus 2. That's it, 0 degrees. That's all. And then I2 now, we have to apply KVL to I2. So I2 is going to be I2 times 1. We start with this resistor. And then plus I2 times J, which is this inductance, right? And then minus, so I'm moving along the loop, right? So when I encounter the voltage source, I see the minus first. So I put a minus 6, 0 degrees. And then I end up with another plus I2 for the 1 ohms, and then I have plus I2 minus J. So I2 gets multiplied with minus J equals 0. So this is the second equation, and I just need to simplify this. Let me simplify this. So I have two I1s, and then two I2s, and then a plus J and a minus J. That's going to be 0. Is that right? Did I make a mistake somewhere? I made a mistake somewhere. Okay, I wasn't careful. Let's do the I2 again. Yeah, I made a big mistake. So as I'm going through the loop represented by, so I got the first equation correct. That's fine. I1 is fixed by the current source, right? Yeah, I1 is set just so that it equals the current source, because there's no loop selected here, right? But then I2, when I'm moving along the loop represented by I2, and in this portion, I have both I1 and I2 passing through those two elements. So really the equation should have been I1 plus I2, right? Times 1, and then I1 plus I2 times J. So I can just put in I1 plus I2 times 1 plus J. Okay, this was my mistake. And then the voltage is fine, minus 6, that's okay. But then now, once we pass here, in this portion of the loop, we have now I2 plus I3 plus I2 plus I3. That's the current in that portion of the loop times the impedance, which is 1 minus J equals 0. So that's equation 2. And I can simplify equation 2 a bit by just putting in the value for I1, right? So I1 is just minus 2, right? Let's do equation 3 first. So equation 3 is going through this loop, right? So equation 3 is going to be, first, the 1 ohm resistor, I have just I3 going through it, so that's I3 times 1. But then I have the other 1 ohm resistor, this one, and the capacitor, I have I3 plus I2 going through it. So that's going to be plus I2 plus I3 times the impedance, which is 1 minus J equals 0. Okay, so this is 3 equations, but I can easily reduce it to 2 equations by plugging in the value of I1. So let's do that. So right, so if I plug in the value of I1 here in the second equation, I end up with, so let me take 6 to the other side. I end up with 6. And then I plug in the value for I1, which is minus 2. Minus 2 times 1 plus J. I take it to the other side. I end up with plus 2 times 1 plus J. Okay. And then let me write the equation. So it's going to be I2. I2 is going to be multiplied by 1 plus J. And also I2 is going to be multiplied by 1 minus J. So it's going to be 1 plus J plus 1 minus J. And then I3 is just going to be multiplied by 1 minus J plus 1 minus J I3. Right, so I can simplify this a bit. J plus J minus J is going to be cancel out, and I end up with 2. So this is going to be the first equation. Let me simplify the other side a bit. So this is going to be 6 plus 2, 8. So it's going to be 8 plus J. This is equation 1. And then in terms of I2 and I3, and then equation 2 is going to be, well, I2 is just going to be 1 minus J I2, and then I3 is going to be 1 plus 1 minus J I3 equals 0. That's the second equation. I can simplify it to 2 minus J. Okay, so 2 equations, 2 unknowns, and I just need now to write it in matrix form. So it's going to be I2, I3. I'm solving for what? I0. I0 is just I3. Right, once I know I3, the negative of I3 is going to be I0. Right, so writing this in matrix form, I get 2, 1 minus J, and this is 1 minus J, 2 minus J, and this equals 8 plus J, 0. So let me call this matrix, I don't know, let's call it V. Just, it doesn't mean that this is a voltage, just from the, oh sorry, let's call it Z. This doesn't mean that this is an impedance, this is a matrix, right? So it's just from the analog to Ohm's law, where I, current times impedance, gives me something, voltage, right? So this, I call this V. This doesn't mean that this is a voltage, this is just a column vector. I just call it V, right? Because when I go to MATLAB, I want to define those matrices and column vectors. So I have to call them something, right? So I'm doing that for that exercise, right? I2, I3 is just equal the same matrix, 2, 1 minus J, 1 minus J, 2 minus J, inverse times 8 plus J, 0. Let's go to MATLAB and do this. So I'm moving to MATLAB and I'm gonna do the calculation now. We said we called the matrix Z and it was 2, 1 minus J, go to the second column, 1 minus J, 2 minus J, that's it, gave me the matrix, and then the column vector is gonna be 8 plus J, second column 0, and then the current I1 and I2 is just gonna be the inverse of that matrix. Oh, just I can use the inverse function. Matrix multiplication with V, and I get the solution. I just take its absolute value and then I take is this correct? Let me double check something. Yeah, I double checked and I think there's a mistake here. The mistake is that I took here 6 to the other side, and then I took I1 was 2, right? Minus 2. So minus 2 times 1 plus j, take to the other side, you end up with 2 times 1 plus j. So you end up with 2 plus 2j. So this is actually 8 plus 2j. Okay. Yeah, I noticed the result I didn't get, what I got was not correct, right? So this is 8 plus 2j, 8 plus 2j. So I have to be careful with those small mistakes. So going back to MATLAB, I have to go and correct stuff here. So I just have to correct V. So Z is the same. Right, so let me clear this. Z is the same pretty much. V needs to be corrected. So V equals 8 plus 2j, next column 0, right? And then yeah, I equals inverse Z, all right? And then I take the magnitude of that to get the current, the magnitude of the currents, and then I take the angle of that. I need to take the angle of that, right? But I need to convert it to degrees, so I divide it by pi, multiply it by 180. And what I'm interested in is I3, right? I3 is going to be, right? Right, so 4.61 is I2, and then I3 is 2.916, and the phases are minus 12 degrees and 149.036 degrees. Right now, going back to my board, we said we found that I2 equals 4.11 minus 12 degrees, and then I3 equals 2.916, 149.036 degrees. But then I always said is going to be minus I3, so the current is going to be minus 2.916 149.036 degrees. What did we find it to be in nodal analysis? Okay, so we said when we deal with phasors, we don't like to have the magnitude of the phasor be negative. How can we fix that? I can fix that by just adding 180 or subtracting 180 to this, right? So what I can do is I can say it's equals 2.916, then get 149.036 minus 180 degrees. I could have added 180. It's going to be the same thing. So 2.916 was 149.036 minus 180. So it's one. Let me go back to MATLAB. 149.036 136 minus 180, that gives me, yeah, minus 30.964. So that gives me minus 30.964. Equivalent, we got a result that is equal, within rounding errors, equal to what we got from applying nodal analysis. All right, so that's the loop analysis technique. All right, so the next technique we want to review is the technique of superposition. And in superposition, we take advantage of the fact that circuits are linear, meaning we can calculate the response of our circuit with respect to the two sources separately, and then once we get the result due to the two sources separately, we can add them together to get the complete response. So I have two sources, so I can do two different calculations. So I start with the current source, J1, and then I have the current source to 0 degrees. And then instead of the voltage source, I put in a short circuit. I make the voltage source 0. How do I make a voltage source 0? I make it short. Then I have I have a resistor here, 1 ohm. And then I have the current IO0 prime. This is the response current due to just the current source, 1 ohm minus J. So I find this current, and then I make the current source 0, meaning I make it an open circuit. So this becomes an open circuit. But then I put in the voltage source now, 6 volts, 0. And then now I find the response that I'm calculating, IO double prime. This is the response due to just the voltage source on its own. This is how you apply superposition, right? And then the total response is just going to be the sum of the superposition responses. So it's going to be IO0 prime plus I0 phasor double prime. Okay. So this is the technique of superposition, right? So let's apply the technique of superposition. Let's first find the current due to just I0 due to just the current source. We're going to apply what's called current divider. Just a review of current divider. If you have a current source I, and then you have two resistors R1, R2, you're interested in the current in a certain branch, right? So I1. So then I1 is going to equal to R2. R2 could be like a bunch of resistors in parallel. It doesn't have to be a single resistor. It's going to be R2, the equivalent resistance of those bunch of resistors. So I1 is going to be R2 over R1 plus R2 I. This is what's called the method of current divider. Contrasts with the method of voltage divider. When I have V, then I have R1, R2. Say I want the voltage across R2. So V2 is going to be R2 over R1 plus R2 times V. Notice in voltage divider, we take in the numerator, we take the resistance of that represents that's associated with the voltage we're trying to find. In current divider, we take for the numerator, we take the equivalent resistance of everything except the resistance through which the current we're interested in is passing. Okay, so let's apply current divider. So I0 prime is just going to be, well, the current is going to be 0 degrees, right? And then we have to take the equivalent resistance of everything except the 1 ohms where I0 prime is passing. So it's going to be 1 minus J in parallel with 1 plus J. 1 minus J in parallel with 1 plus J. So it's going to look like something like this. 1 minus j in parallel with 1 plus j divided by 1 minus j in parallel with 1 plus j plus 1. Right? We can calculate this easily, right? 1 minus j parallel 1 plus j is just what? Is 1 minus j, 1 plus j over 1 minus j plus 1 plus j. J cancels with j and I end up with this is like a number with multiplied by its complex conjugate, right? So I end up with 1 squared plus 1 squared, 2 over 2, 1. So 1 minus j parallel 1 plus j is just 1. So I end up with I0 prime equals 2, 1 over 1 plus 1 equals 2 over 2 equals 1. So I0 prime phasor equals 1 amps. Okay. Now we want to go back and solve for I0 prime prime. Right? Here in this case, we want to use the voltage divider. We have a voltage source, right? So we want to find, let's call this V2 prime prime. If we find V2 prime prime, just divide it by 1 ohms, you get I0 prime prime. I mean, the relationship between V2 prime prime and I0 prime prime is simple. It's just a factor of the resistance there in that branch, which is just 1 ohms. Okay. How do we find V2 prime prime? We just do voltage divider. We take this equivalent impedance divided by the total impedance. So let me write it down. So V, what did I call it? I called it V2 prime prime. Okay, so V2 prime prime equals 1. So what's this impedance here? This impedance here is 1 ohms parallel 1 minus j. Right? And then I have here, I take this whole thing and I find the total impedance, which is this whole thing in series with 1 plus j. Right? So the voltage divider is as follows: 1 parallel 1 minus j divided by 1 parallel 1 minus j plus 1 plus j times 6, 0. Okay, so I can manipulate this. I can end up with what would this be? This would be 1 minus j, their product over their sum, over 1 minus j plus 1, 2 minus j. So this thing would equal, right? So let me do this here. 1 minus j over 2 minus j times 2 plus j times 2 plus j. I end up with, right? So I end up with the denominator being 2 squared 4. This is a number with complex conjugate, so it's going to be 2 squared, which is 4, plus 1 squared, which is 5, and the numerator is going to be 2 plus minus j times j is 1, 3, and then minus 2j plus 1j is going to be minus j. So this is going to be 3 minus j over 5 over 3 minus j over 5 plus 1 plus j, 6. Multiply numerator and denominator by 5, I end up with 3 minus j over 3 minus j plus 5 plus 5j, 6. I end up with 3 minus j over 8. 5j minus j is going to be plus 4j times 6. I can manipulate this further. I end up with 6 over 4. 3 minus j over 2 plus j. Right, what is this? This is going to be 3 minus j, 2 plus j over, 2 minus j over 2 plus j, 2 minus j. So the denominator is going to be 4 plus 1, again, 2 squared plus 1 squared, which is 5, and then the numerator is going to be 3 times 2, 6, minus j is going to be minus 1, it's going to be 5, right? And then minus 2j minus 3j is going to be minus 5j. So I end up with this being 1 minus j. So I end up with 6 over 4, 1 minus j volt. I multiplied by, divided by 1 ohm to get amp, so I0 double prime is going to be 6 over 4, 1 minus j amp, right? So now the IO is going to be IO prime plus IO double prime, which is going to be 1 plus 6 over 4, 1 minus j. If you do the math, this turns out to be the same thing. Turns out to be 2.9155 angle minus 30.9638 degrees. We should expect to get the same value, regardless of the technique that we use. The fourth technique we want to review now is the technique of source exchange, which is really very similar to the Norton and Thevenin analysis techniques, equivalent circuit techniques. We just have to kind of like look at a source and try to kind of lump it with some impedance so that we can convert it from one form to another, from a current source to a voltage source. I'll show you how to remind you how to do that. I hope you studied it in Circus 1. But anyway, it's very simple. It's all based on Norton and Thevenin, which we will cover next too. All right, so let me do the circuit again. So the circuit is again resistor 1, inductor J, and then a current source of 2, 0 degrees. I have a voltage source of 6, 0. Then I have R1, and then I have, what else do I have? Let me remind myself. I have 1 and minus J, 1 and the capacitor. So I have here 1 and then minus J, which is the capacitor. Right? So the technique of source exchange is just, we want to combine the sources into one source. So what we could do is we can look at this source by itself here with this impedance in parallel with it. And we want to convert this into a voltage source with an impedance in front of it. Again, like I said, this is very similar to kind of converting between Norton and Thevenin. It is exactly that thing. It is exactly a matter of just conversation between the two different representations. So you take a current source in parallel with an impedance, you change it into a voltage source in series with an impedance. You take a voltage source in series with an impedance, you convert it to a current source in parallel with an impedance. Okay, so as a voltage source, what would this portion look like? This portion would look like, well, I mean, the current is going to pass through those two impedances, 1 plus j, right? So the voltage source, as a voltage source, this source is going to look like 1 plus j times 2. So this is the voltage source, volts, right? And then the impedance in front of this voltage source is going to be the equivalent impedance of this Norton circuit. So it's going to be 1 plus j. So I'm going to have 1 and again j, right? So, and then I'm going to have minus plus 6. Then I have 1, 1 minus j, right? Now I'm still trying to find I0. Now I can sum up those two voltage sources. So what I can do is I can say, hey, let me sum up those two. So I end up with 6. Why can't I delete? Right? 6 plus 2, 1 plus j. Right? Volts. Right? So I just summed up this voltage source. Now I can take this and can turn it back into a current source. Right? So this is like a Thevenin equivalent. I need to turn it back into Norton equivalents to turn it back into a current source. I just how do I turn this into a current source? I think what happens if I short this? All the voltage is going to be applied on to this impedance. So I'm going to get a current source of what? Of 6 plus 2, 1 plus j, over that impedance, over 1 plus j amps, this is the current source, and then the impedance is going to be 1 and plus j. It's an inductor, it's positive. This is what it will look like, and then 1 ohms, and then I0, right? And then 1 minus j. This is a resistor. Okay, now this we can easily solve using current divider. Right? So we can do a current divider. What we can do is we can this is minus j. Right? So in this case, I0 is going to be current divider, right? So it's going to be like the equivalent impedance of all the branches except the branch we're interested in. So it's going to be those are two in parallel, of course. So this is going to be I1 plus j parallel 1 minus j, right? Over the sum of all the impedances, 1 minus j parallel 1 plus j parallel 1 minus j plus 1 times the total current, which is 6 plus 2, 1 plus j over 1 plus j. So we need to calculate this, and once we calculate this, we should see that we should get the exact same result. Okay, so this is the technique of source exchange. I guess we're out of time. I'll continue this example and more examples next time. Thank you, guys.